We're at part 3, other aqueous reactions. We've talked about precipitation reactions and complete net ionic. There are other ones that fall into this category. Well, one is gas evolution. That means a gas is formed. And what you'll see is this one actually is a two-step. This is the reaction of an acid with sodium bicarbonate, so baking soda and vinegar. You generate carbonic acid, which then immediately decomposes into water and CO2 gas. So you could actually end up with a net ionic reaction there. Same thing with this process is instead of forming a precipitate, you're forming a gas. And so the net effect is this one is still aqueous, and aqueous. You're generating a gas, so you would generate a net ionic equation as well. One of the reactions that we've talked about back and forth is a strong acid or base species. And strong acids dissociate completely. We gave you the list of them. And the definition of a strong is it dissociates completely. Weak acids and weak bases dissociate partially. And they are partially, okay, they are weak. And remember, I told you about the double arrow, the two-way arrow. The difference between a strong and a weak is this is a strong electrolyte, and this is the weak acids are a weak electrolyte because they don't dissociate a whole lot. When you get into 1212, you'll do a couple chapters just on acid. Now, formulas for acids are generally written with the acidic protons listed first. So we've talked about acid-base reactions. Now the question is what's an acid? According to the Bronsted-Lowry acid system, which is the one we use, an acid donates a proton, or it's a proton donor. The opposite is the base, which accepts a proton. So when you're talking about acids and bases, you're either giving one up, acid, or you're accepting one, which is a proton. An acid-base reaction is also known as a neutralization, and it's a reaction where you have an acid plus a base react to produce a salt, not table salt, but a salt, ionic compound, and water. So the biggest thing is look for the water and then you say, oh look, here's your salt. Salt is the salt, ionic compound. So this is my acid, this is sulfuric, which was on your list. And, oh wow, that's a major typo. It should be KOH. And it should have a 2 in front of it. I'm not sure where that 2 came from. Okay, obviously I need to correct that slide. But this, again, has a pure liquid. So it would then produce a net ionic equation. Because it won't have all the spectators. Everything is not a spectator. So terms associated with acids and bases. H3O plus is your hydronium ion. So if I say there's a hydronium ion, that means there's an acid. OH minus is the hydroxide ion, which you've already learned in your common ion species. HCl is an acid, but it's what's called a monoprotic. Mono meaning one, so it only has one proton. H2SO4, sulfuric acid, is a diprotic because it has 2. So phosphoric is a triprotic because it has 3. Because these are the protons that we're looking at. So together, di and tri are often referred to as polyprotic. Anything more than one is a polyprotic. There are some acids that are can have 3, 4, 5, 6, 7, and on up. So don't think that, oh, you can only have 1, 2, or 3. You can have a whole lot more than that. Some properties of acids and bases. Acids tend to be sour, lemon juice. Bases tend to be bitter, soap. Don't go lick soap. But some of you may have encountered soap. If you wash your hands and don't rinse well, you may taste soap. That's the bitter. Bases tend to be really slippery. Laundry soap is really slippery, as opposed to like vinegar or whatever. Those tend to not be. Bottom line is, I want you to read through these, and you may have like a question, multiple choice, identify, if it's bitter, is it an acid or base, something ridiculous like that. Bottom line is that acids and bases are one of the most common things you encounter. So it's a good idea to know a little bit about them. Okay, the next thing is that when the stoichiometry 2, we do the titration lab. And so there are terms associated with that. Okay, a titration is using a species, a liquid species, in a burette to find the concentration or amount of a substance. And when I say it's a liquid, that I should have said it's a solution we add from a burette. The analyte is what we're looking for. What you're looking for. So the analyte is the unknown. So it's a fancy name for unknown. Okay, the titrant is the solution added from the burette. And here's the thing. There are some reactions where we know what's in the burette, and there are other reactions where we're looking for what's in the burette. So the burette, what's in the burette, can also be the analyte, but it is definitely the titrant. Now the equivalence point is when you have stoichiometric amounts of acid and base added. What it boils down to is your moles of acid equals your moles of base. So that's your equivalence point. That's where you have reacted the moles to moles, which is different from the end point, which you hope are the same thing. But the end point is when the indicator changes color. And that's why you want to pick an indicator that shows your equivalence point. Okay, so the end point is when you're done. You've hit the color change. It's usually color change. Versus the equivalence point, which is when your moles equal your moles. Okay? And this is actually really important because your stomach creates really strong acid. And sometimes you need to calm that down. So antacids are a good way to do this. So in the next section, we will go forward to another type of chemical reaction dealing with oxidation numbers. So you may want to review that if you need to.